thanks for the opportunity to talk about my research a little bit. So my name is Ben. I'm an associate research professor at CMU, or I will be in January. And prior to that, I've been here at CMU almost 4 years as a principal researcher. And prior to that, I was at Google for almost 10 years, where I worked on V8, which is the JavaScript engine in Chrome, and also co-founded the WebAssembly project and worked on the WebAssembly engine inside of Chrome. I'm going to talk about WASM a little bit today because most of my research focuses on that. I would say that WASM research is hot. So there's a lot of publications coming out. There's new researchers joining the field. There's funding out there. There's workshops. There's education going on. Well, compared to other research fields like machine learning and AI these days, maybe it's not quite hot. So we might say it maybe is goodly warm. And I think it's warm in a good way. So towards that end, Heather and I, so Heather Miller pictured here on the left with me, co-founded with me the WebAssembly Research Center here at CMU. And so we've got collaborators across multiple different departments and even across different schools that work on various things related to WebAssembly. In particular, we've got partners such as Dfinity, Shopify, Siemens, and Woven in the NSF that have contributed to being able to support students doing this research. So the quote that I motivate my research by and our research by is, in a software landscape dominated by mobile, untrusted, and semi-untrusted code, how can we ensure applications run safely and efficiently everywhere they need to? There's a couple of different research focus areas, and different faculty members have their specialties. My specialty is mostly on runtime implementation, so on WASM engines and language runtimes, but I do work with collaborators on all these different things here. I'm going to mostly focus and do a deep dive on some of the work that we've done in WASM engine land. It's all motivated by this basic fact. Programs have bugs and sometimes run slow. If we look at tools for dealing with the fact that programs have bugs, there's a lot of static tools like such as type checkers, linters, verifiers, but we need tools also for dynamic analysis too. And by dynamic analysis, I mean running the program, looking at what it does. And so what we've been building in the engine is tools to help with both these things for programs that have bugs and ones that run slow. So we've built something that we call the Wizard Research Engine. It's a WebAssembly engine, so it's the thing that runs WebAssembly code. It was designed specifically for research. So it supports the entire specification as of 3.0, which is still coming out this summer. But the idea is that this virtual machine is architected for experimentation. It's not a product. So it's fast enough, but it's designed to have innovative tooling that allows us to do this dynamic program analysis. And so the main mechanism here is callbacks, which I'm going to briefly dive into. In particular, we use the mechanism called probes. So Wizard has a bytecode interpreter. So imagine the program on the left here, which we're looking at, which is bytecode. This is actually WASM bytecode. There might be a point of interest in the execution, and whenever that point is reached, we get a callback, and then we can attach some logic to the program to do analysis. And then we can look at the state of the program. So this is often that we only have a few places in the program you may want to look at and make that programmable. So the way this works and the way it's made efficient is basically the engine underneath is able to very efficiently check only at points of interest that some logic needs to be done to be able to very efficiently call the user callback and then to be able to execute the original logic of the program. So this is pretty easy to do in an interpreter, and we'll see in a bit that it's that also works in the compiler. And we can also remove the probe too, and removal of probes is also useful for implementing certain things. So for example, the ability to add and remove instrumentation allows us to do a thing like code coverage. So imagine we wanted to know which of these basic blocks are executed. So we would instrument them all by adding probes everywhere. And then the probes, as they execute, they basically mark which of the blocks have been executed, and then they remove themselves. So as the program runs, it actually removes the overhead for instrumentation. And then as the program gets hot, and the dynamic compiler kicks in, the hot code will eventually be compiled and it has no overhead. So it means that this code coverage task can be accomplished with very little overhead. And that's all because we can remove instrumentation at runtime. So using the same mechanism, we can implement a lot of different things. And so all of the basic things that come out of the box with Wizard are all implemented using the same mechanism, whether that's a profiler for loops or branch profiling or function profiling and so on. One issue with implementing instrumentation in an interpreter is an interpreter is a lot slower than a compiler. It could be 30 times slower. So if you measure the overhead of adding instrumentation on a very slow baseline, it's going to look like it doesn't add much. And so in order to be able to get a true picture of what the actual overhead is, we need to implement a compiler. So that's one of the things that we did, and I won't be able to go into all the details. That's why we write papers. You can go into details. But Wizard has a baseline compiler. It's basically a state-of-the-art single-pass compiler, and it interacts very nicely with the interpreter and also supports instrumentation. In particular, as it goes along compiling the code, it injects instrumentation into the compiled machine code. And it understands instrumentation and can generate efficient instrumentation when necessary. And that makes a big deal, a big difference. So that can reduce the overhead of instrumentation by 10x or more, and it can sometimes be faster than other solutions. So doing instrumentation at the bytecode level is quite tedious. You have to understand how the bytecode works. You could make mistakes. So to address that problem, to make instrumentation a lot easier for most people to write, we came up with a domain-specific language for instrumentation called WHAM. So instead of writing stuff that deals with bytecodes one by one and all that, you can write a little script, and the script will get fed into our tools that will then generate either an instrumented application, which you can run anywhere, or it will generate a monitoring module that you can run on Wizard. And this language is actually inspired by other monitoring languages that have come before it, such as dtrace. So it's a bit familiar to people who have done this before. And nowadays, we're working on dynamic optimizations for how we make that go fast, with the ultimate goal of making it clean and nice, and be able to write these in a very expressive way, and yet they run fast. And that's all I wanted to dive into. Thanks for your time.